So yeah, thanks for the kind introduction. So I'm going to be talking about reservoir computing. This is a topic that is going to be covered later in this meeting as well. So I will try to give a little bit of background about reservoir computing for people who aren't very familiar with it. And in particular, I'm going to be interested in applying reservoir computing to two particular contexts. One is the context of network inference. And in particular, I'll be interested in inferring networks of neurons, and I'll tell you more about that. And later I'll talk about reservoir computing in the context of dynamical noise, and in that context, the deterministic skeletons will hopefully make sense over there. Just quick shout out to people I've been doing this work with. So this work has largely been done, has entirely been done in collaboration with this set of people. Amitabh Banerjee is a grad student at University of Maryland right now, and Professors Brian Hunt, Raj Roy, and Ed Ott have been instrumental in guiding all of these research directions. So with that, I'm just going to start off and get right into it. So reservoir computing was first developed kind of independently by Jaeger and Maas around 2001, 2002. And they're also known by other names such as liquid state machines, echo state networks, and other things. But the essential thing is that they're very, very effective when working on data from dynamical systems. And the key idea is to train a high dimensional dynamical system, which is the reservoir, to emulate the dynamical system that is governing the input data. So for example, if your data is given by some x of t, the entire idea is that you have some sort of thing over here, which I'm going to call the reservoir computer. And let's just abstract it out just as a black box for the moment. What you want to do in the training phase is generally you want to feed in x of t to this reservoir. You want to drive the reservoir with your data. And you want to train this system to be able to output the next time step. Now, I should just say at the get-go, I mean, this is not necessarily the only way you can set up a reservoir computer, but this is often very, very common architecture for using reservoir computers. And this is largely the setting that I'll be interested in today. So in the training phase, what you're trying to do is you're trying to train the reservoir to learn the map from x of t to x of t plus 1. And this configuration are called the open loop reservoir. And so you want the open loop reservoir to learn this map. And then what you can do in the so-called testing phase is you can go to like a closed loop system, where what you're basically doing is whatever x of t plus 1 was generated, you feed that back in. That will generate x of t plus 2, which can again get fed back in, and it'll generate x of t plus 3, and so on. So essentially what you hope is that this closed loop system, which is now an autonomous system, is going to emulate the dynamical system that generated your data. And this is essentially the very high level picture of what you try to do with reservoir computing, at least in the context of prediction, right? But let's just peer into this a little bit more. Let's just get down a little bit more to the specifics, but let's not, it won't be too detailed at all. So what is the reservoir computer? So generally a reservoir computer has three main components. The first is basically this W-in, which is a fixed input matrix. This is not varied, it's not trained, it's randomly chosen just by setting one hyperparameter or so. This input matrix basically takes your input data, x of t, and projects it onto some high dimensional dynamical system, which is the reservoir. And the state of this reservoir I represent with the vector r. And so the dynamics of the reservoir, when driven with the input data, are basically given by this equation over here. So r of t plus 1 is some nonlinear function phi acting on w in times x and r. So basically just taking the input data x, you're projecting it with through the fixed input matrix to the reservoir state, and then this is just some dynamical system now. Okay, so this is just the driving part. And what you want to do, as I said earlier, is that you want to train the system via a single readout layer, which I'm calling W out over here, to map to x of t plus 1. So essentially W out is a readout matrix, which is trained such that x of t is W out times r. And the way you do this is just by minimizing something that looks like this. You have two terms over here. One of them is just W out times r minus x of t, and I'm just summing this over all time. And the second term is just a small regularization term just to prevent some sort of overfitting. So the training phase, what you're essentially doing is you just drive the reservoir with your input data, and you train a single readout layer for it to map to the next time step. And of course, the advantage of using reservoirs is because you're only training a single readout layer as opposed to other forms of, say, deep learning, where you might have to do backpropagation or backpropagation through time over multiple layers and so on. Because it's just a single layer, the training can just be done by a single time-efficient least squares regression step, right? And so that makes the training part fairly straightforward for a reservoir. And then when you go to the testing phase, when you go to the closed loop, what you're essentially saying is that after you get an R, you convert the R back to X via the readout matrix, and this X just gets fed back into the system. So these two sets of equations then define this autonomous dynamical system, which is just the closed loop reservoir. And if everything's gone right, hopefully it's going to emulate the dynamical system that generated your data. Okay, now reservoir computers have been used for all sorts of problems relating to data from dynamical systems. I mean, they have been used in other cases as well, but a large focus really has been when your data is coming from some sort of a dynamical system. And there are all sorts of problems, and I wasn't going to go ahead and list all of them. I've just listed thrown out a few over here. There's chaotic time series prediction. You can do some sort of network inference. You can do data assimilation. You can reconstruct some larger system states. There's really a lot of things you can do. Chaotic time series prediction is basically following the framework that I described earlier. And this is something that I will get back to, but in the second half of my talk. But in the first half, what I really want to focus on is network inference. And largely, I'll talk about the framework that was developed by my colleagues at the University of Maryland, basically in these papers. So let me just state the problem first, right? What is the problem of network inference? The essential idea is that now, instead of just a single time series, you have n different time series as a part of your data. So you have x1 of t, x2 of t, all the way up to xn of t. And this data is coming from some set of nodes. But what you actually want is, instead of these nodes, what the underlying system is actually some sort of a network. And so what you want to do is you want to take the data and only the data and somehow infer what this underlying network structure was. So you want to get from here to here. And I guess keeping in theme with the topics of this meeting, the way we're really going to be looking at it in practice today is I'm going to be looking at what happens when this data is actually coming from some sort of neural data from a tiny worm. And the other more general settings have been looked at in this paper, but really this particular setting is going to raise some very interesting issues, and that's what I'd really like to talk about today. So let's just understand where we're getting this data from. Some of you may have already recognized it just from this image. This worm is basically C. elegans. It's an extremely common model system in biology. It's not actually that big. That's not real size. It's actually just around 1 mm, but it's just extremely ubiquitous in all sorts of studies, just because it's been a very well-studied organism. And for our purposes, what's important is that the entire connectome of this organism has been mapped out. By connectome over here, I basically mean the connectivity of all of the neurons has been completely mapped out. And so there are 302 neurons in total. And it's for what we want to do, it's kind of important that we're working with a system where the connectome is known, because we would want there to be some kind of underlying ground truth for us to know whether our results are really working or not. But of course, in practice, we'd hope to be able to apply these results to systems where you don't know the connectome and hopefully actually infer the connectome. Okay, so what kind of data do we have in particular? So the data that we're going to be using today is obtained from calcium fluorescence imaging in the moving worm. And there are some advantages and disadvantages to using calcium fluorescence imaging. One advantage is that you can really image simultaneously a very large number of neurons. If you want to do this via some sort of electrodes, it's much more resource intensive to be able to actually obtain signals from a large number of neurons. And even then, you can't really measure a lot of neurons simultaneously. So one advantage of using calcium fluorescence imaging is that you can really get a lot of data simultaneously. The issue, though, is that it then becomes low temporal resolution, because the dynamics of the calcium ions, they have their own time scales, and it just is much slower than the time scale of like a very sharp neural spike. And of course, C. elegans itself is known for not having very sharp spikes at all. So really, this data is going to have some fairly low temporal resolution. And for that reason, really, people often think that calcium fluorescence imaging really isn't very useful for something like network inference. But this is actually going to be a crucial point later, so I just want to reiterate that a little bit more. The neurons in themselves, which are generating these spikes, have complex dynamics of their own. They receive signals, they integrate signals in certain ways, and then they have some own internal dynamics of various ions by which it eventually decides when to send a signal. All those dynamics are just getting reduced to a single observable variable, which is just the fluorescence intensity of these calcium ions. right? And this point is going to kind of be crucial when I go on later ahead. So, okay, so what does this data really look like? It looks something like this. This is just a bunch of neurons, and this is what the time series look like. It's just this one variable of this fluorescence intensity. As you can see, the data is not even very long, and a lot of the neurons are really just quite silent. So this is a moving animal, and so what it turns out is that the motor neurons are really much more active. And so our focus for the purpose of what I'll be talking about today is just look at the reduced network of the active motor neurons. And further, these neurons, and well, C. elegans largely almost entirely presents a strong left-right symmetry, which is inherited in the network as well. And so what we're going to do is we're going to look at a further reduced network of 8 pseudonodes, where each pseudonode is just a combined left and right pair of neurons. So instead of looking at 16 active motor neurons, we'll be looking at an 8-node network with these 8 pseudonodes, which basically looks something like this. That's like the goal of what we want to do. We want to be able to reconstruct a network that looks something like that. Okay, so hopefully I'll give you some idea about where I'm getting my data from and what my data kind of looks like and what the hope is. Let's just now actually get back to reservoir computing, and let me tell you how do you actually do network inference in this context. And this is basically just a framework developed by Banerjee and others in the papers that I had discussed, that I had showed a little while earlier. So what's the essential idea? So over here, we have some kind of dynamical system, which is some network-based dynamical system. And the form of link inference that we're going to be interested in is the causal effect of one node on another. So what does that really mean, right? So let's say I take this one node and so let's assume I don't know the network, and I take one node and I can perturb it in some fashion, right? So I'm just representing some sort of perturbation by just darkening the color of this node. So what would happen if I perturb this node is that over short times, this perturbation is going to spread through the network. And this perturbation will first hit these 2 nodes. Now, of course, if I wait for longer times, this perturbation will eventually spread further and further in the network. But at short times, it will only affect these 2 nodes. And that would basically be indicative of the existence of these 2 links in my network. Right? So this is what I mean by causal inference. If I'm looking at some sort of perturbation, how does that causally link to other nodes? Right? Now, of course, in being able to describe it this way, I'm kind of saying that, let's say I had my C. elegans and I could inject something in one neuron and I could see how other neurons respond. I can't really do that, right? My goal is to be able to do that non-invasively and from just the data. So if I just have access to the data, can I somehow, in effect, do something like this kind of a perturbation? And the answer is going to be yes. And the key idea is to be able to use the reservoir computer, right? So what you do is you train the reservoir computer once again to learn the one-step map. So now instead of just inputting one time series, I input all n time series. And I ask the reservoir computer to learn the t+1th step of all of these n nodes, right? And so if my training has been done appropriately, the trained reservoir is going to learn the one-step map, which means that my reservoir can now behave as a proxy of my original system, right? So instead of worrying about perturbing nodes in the actual C. elegans network or in the actual network that I'm interested in, I can just perturb nodes in my proxy system. So I can now perturb some node, and I can see how those perturbations propagate. And that's essentially going to be able to tell me what things are connected to what other links. And so you can basically do something like this to obtain a score for every possible edge, which I'm just going to represent by S subscript I to J. So you can basically obtain a score for all possible edges. And that's really via some sort of estimate of this Jacobian element, which I'm estimating in my proxy system through the reservoir. Okay, so what happens if you actually do this? So let me just take a simple toy model first. So we're going to take Lorentz model oscillators. So every node here is just the Lorentz 63 model, just the simplest model that people use all the time whenever they're interested in studying chaos. So every node over here is now a Lorentz model, and the links basically correspond to some kind of coupling that I've introduced between the variables of the Lorentz model, right? And so if you run this entire idea, which is you take the reservoir, you train it on data from the Lorentz, all of this n node Lorentz oscillators, you learn the one-step map, you perturb nodes in this proxy system, and you obtain scores for each edge, you basically obtain something that looks like this. So you obtain a set of scores, you see one set of larger scores and one set of smaller scores, right? And so what you might then do, which is very reasonable over here, is you say, okay, I can now choose a threshold. And I can say that everything above this threshold, I'm going to say is going to be a link. and everything below the threshold, all the scores corresponding to these, all the edges corresponding to these scores are not really edges in my system. Only these scores correspond to actual links. And indeed, you can actually peer into this and see that that is actually the case. So if I look at the distribution of scores for things that are actually links, it is indeed this entire distribution over here. And if I look at the distribution of scores that are not links, it is indeed the distribution of scores over here. So if I chose a threshold over here, I can correctly identify all the links in my system. And okay, so this was a very simple toy model of just Lorentz oscillators. Before jumping into C. elegans, let me just make a slight modification to this toy model itself. Because what turns out is that this is a very, very idealized scenario where you have this wonderful separation, and that generally is not going to be the case. In fact, a lot of the literature where people try to do network inference-based techniques, they often end up considering scenarios where you get such good separation, but in practice, that's not actually going to be the case. So a simple modification I'll do to this toy model is that for each node, instead of measuring x of z, xi, yi, and zi, what I'll do is I'll just consider that I can only observe one combined variable, which is xi square plus yi square plus zi square with some normalization. So now for each node, where each node is a this Lorentz attractor embedded in 3 dimensions with some perturbations, each node has an x, y, and z variable. Let me assume that I can't actually observe the 3 variables independently, but I can only observe this combined variable. It turns out that if you do this, the score distribution is not that nice at all. And really this, so as you can see over here, there's really just no good choice of a threshold, right? Because there's no gap in this distribution of scores. So you just don't know what the obvious choice of the threshold is. And I know I'm showing this specifically for using reservoir computing and link inference through reservoir computing over here. But you can do this with, say, transfer entropy, and we think you can do this even if you do this with other methods. Whenever you have something like partial measurement, you're going to potentially have an issue like this, where your score distribution is just not going to have any clear separation, right? And indeed, you can really peer into this distribution as well, and you can say the distribution of scores corresponding to links and the distribution of scores corresponding to non-links is really just merging into each other. And so you can make some choice of thresholds, which will give you links, but they won't give you all the links. And you can choose some other choice of thresholds, which might be smaller, which will give you some more links, but will also give you some false positives, right? And so the question really is, how do you actually meaningfully choose a threshold, right? And I should say, I've been doing all this with just the Lorentz model and this toy version of a Lorentz model, but really this is what happens with C. elegans as well. So if you actually take the data that I had showed you earlier, you actually feed it into the reservoir, and then you train the one-step map, and you do these perturbations, and you obtain scores. You obtain a distribution that looks like this, where you can see, hey, maybe there are some gaps, but really, if you knew what were links and what were non-links, you'd see that there are a lot of links that are really in this cluster over here. And so once again, the real question is, how do you meaningfully choose a threshold, right? Ideally, maybe you'd want to choose a threshold something over here if you want to get a large number of links. But really, the question is, for various choice of thresholds, can I really know how many links will I get and how many non-links will I get? Can I ascribe some sort of statistical certainty to this entire process in a case when my distributions of scores just merge into each other, right? And so that's essentially going to be our goal, at least for the first half of my talk, which is how do you separate the distributions without having access to any underlying truth, without knowing a priori what are links and what are non-links, just from this combined score distribution, can I actually somehow reconstruct this, right? So that's going to be the essential question. And what I'm going to claim is that you can do this via a method that we are calling causality destroyed surrogate data, right? And so the claim is really that the CDS data is going to follow the same distribution as the non-link scores. And so if I can do that, then I can really proceed from there. So let me explain how I actually construct this CDS data. For that, let's first revise what we've actually done so far, right? So we have this some set of nodes. These nodes have some time series. And for now, let me just look at this one node at a time. Let me just select a certain node, right? And now you can do this entire reservoir training process and node perturbation and so on and so forth to obtain a set of scores for various nodes pointing into this node, right? So I can obtain a set of scores associated with all of these potential links. And as we said, these scores have some distribution, and some of these larger scores are good, some of the smaller scores are bad, but these distributions have all merged into each other, and we want to know what to do, right? And so what we're going to do to construct the surrogate data is something very similar, where once again, let me select this node, but we're just going to do a fairly straightforward idea, which is just, we're just going to shift this particular time series. And after we've shifted the time series, we're then going to calculate the scores pointing towards this node, right? It's a fairly straightforward idea, and people have done variants of this in the past. But what we're going to be using crucially over here is that we're only going to shift one node at a time. And it turns out that if you're actually working with data like C. elegans, where you don't have too much data, scrambling all of the time series just doesn't work out. And I can go into that after the talk if there's more time. But really what we found was ideal over here, and what was crucial over here was that we consider a node, one node at a time, we just shift this time series, and then we calculate all the scores of the other nodes pointing into this node. Then we can choose another node, shift that time series, and find the scores pointing to that node, and just proceed so on and so forth. And we get a bunch of surrogate scores. And if you look at the distribution of these surrogate scores, what I'm going to claim for now is that this distribution is really going to very closely approximate the distribution of the non-linked scores. And that's kind of intuitive, right? Because what we're really measuring through all these scores is some causal dependence, which is if I perturb a node at short times, how do these perturbations propagate? And so if I've just shifted this time series by some large amount, any perturbations or any fluctuation in the dynamics happening at these nodes is not going to affect this node at short times, but indeed any so-called effect will only be at this much larger time. So at short times, these things are basically going to not be causally linked. And so the scores that I obtain over here are going to be similar to the non-linked scores. And so in practice, what we really do is we shift this time series by as large an amount as possible. We shift it by half the length of the entire time series available to us, and then we just cyclically shift it. So the second half just comes back to the start, right? But essentially, the idea is just the following. We just shift the time series and we look at scores pointing towards that. And that gives us a surrogate distribution, which if everything's all in good, it'll match the non-linked distribution. So let's now really verify if that is actually the case. Let me go back to C. elegans. This is the distribution that we had obtained for C. elegans. And so now if I just do this entire process and I actually look at the distribution of surrogate scores, I see something that looks like this. Okay, now this plot is starting to look a little messy. So let's just clean it up a bit and let's just look at the non-links and the surrogates for now, right? And so what you really see is that indeed the non-linked score distribution and the surrogate score distribution are really quite similar to each other. Now, of course, there are some fluctuations. After all, there are going to be some finite size effects if I'm going to be sampling from a distribution. And so really to just try to ascertain a bit better if the distributions are matching, what we're just going to do is we're going to calculate the cumulative distribution function of the surrogate scores and the cumulative distribution function of the non-linked scores, and I'll just plot one versus the other. And as you can see, they're basically on the y equal to x line, which is essentially saying that these two distributions are essentially identical, right? And so you get a very close agreement between the surrogate scores and the non-linked score distributions, which basically means that this picture, the schematic that I had drawn out earlier for you really goes through. And so now what I can do is if I'm actually given a particular score that I obtained for any candidate link, if I know what this distribution looks like, I can find the probability that that is not a link. And hence I can also try to ascertain what the probability of that is to actually be a link. And I can do all of this without having access to the truth and by only looking at the data essentially, right? And so you can really use a surrogate to obtain p-values and confidence probabilities of any possible candidate link. And then you can really see that you can then actually get a good number of true positives and a small number of false positives. But really what's essential here is now that you can quantitatively really tell how many true positives and how many false positives might you get, right? Yeah, and so all that really seems to work out through the usage of this causality destroyed surrogate data. And so just to conclude this half of my talk, reservoir computing really can be used quite effectively for network inference, and link inference scores for partial state measurements is in itself insufficient to choose threshold and certain links, but you can use causality destroyed surrogate data to quantitatively assess the statistical certainty of link inference from scores. And we think that this is going to be something that is not really just specific to reservoir computing as a means of network inference, but really, hopefully it's going to be able to be quite applicable to other methods as well. Now, hold on a minute, right? I mean, there's potentially an issue in what I've said so far, right? And let's talk about that. Oh, I guess before that, I should just say that there are the two references for the general technique but the work in the context of C. elegans itself is still being written up and will hopefully be published in the coming months. Okay, so now back to that objection that I was stating, right? C. elegans is not a deterministic system, right? But a trained reservoir must be a deterministic dynamical system. There was no noise in those equations that I told you. Now, when I say that C. elegans is not deterministic, I don't mean to say that this worm has free will, right? I don't want to get into any discussions like that. But at the very least, neurons themselves are subject to Poisson fluctuation spikes. At the scale at which the worm is operating, there are also the thermal fluctuations and all sorts of other things which are really driving the dynamics, right? And so my reservoir computer clearly can't learn a map that corresponds to the actual dynamics because the actual dynamics are stochastic, right? So a deterministic system, I'm only learning a deterministic system, but I'm trying to learn a stochastic system, right? And how does that really work out, right? How do reservoirs work with noisy data? And more generally, how do reservoir computers behave in the presence of noise? So this is going to be like what I'm going to try to address and understand a little bit more in the second half of my talk, right? Which is really how do reservoir computers behave in the presence of dynamical noise? And really, this is dynamical noise that we're interested in because these Poisson fluctuations are really affecting the dynamics themselves. This is not just some noise in your observations. This is really noise in the dynamics itself, right? So let's just try to understand what happens when you try to use reservoir computers with dynamical noise. So just taking a step back for a moment, what kind of noises might we be looking at, right? I mean, noise is really pervasive in systems in all sorts of scales, right? Just brief mentioned this in the previous talk as well. I mean, really, you have all sorts of fluctuations and uncertainties that are there in your system dynamics itself. And it's really present at all sorts of scales, right? You have right from quantum fluctuations at the smallest possible scales to you could be looking at the weather and you have some very high dimensional chaos, which is just completely unpredictable with the variables that you're measuring, which is also effectively just noise, right? So we've seen that reservoirs seem to work effectively in noisy environments, but what I wanted to really try to zero in onto the question is, can reservoirs be used to actually filter out the noise and obtain a noise-free signal, right? And why would you want to do that, right? First of all, well, of course, if you have data that only has some large amount of noise in it, it's really going to be hard to understand what kind of underlying physics exists in the system. If ideally you could somehow filter away all of that, the dynamical noise, and you could obtain a clean system, then you can actually start building physical models. You can actually start using all sorts of various data analysis and model building techniques and actually try to understand what's going on, right? So filtering out the noise is going to be quite essential. And what we would ideally want, right, our ideal goal would be to be able to obtain a general purpose noise filter that doesn't require access to clean data and works irrespective of the form of noise. Because when you're actually observing that system, you don't have the choice to turn off the noise just for the purposes of your training data, right? Your training data is noisy. That's all the training data you get. And you don't even know the form of noise, right? So without knowing the form of noise, without having access to clean data, what can you do? And what I'm going to claim and show is that reservoir computers work excellently as this general purpose noise filter. So let's just try to understand a little bit more about what I mean by noise in this case, right? There are generally two types of noise that people look at. There's observational noise and dynamical noise. Observational noise is a very well-studied problem. People have really looked at this quite a lot. And what essentially happening in the case of observational noise is you have some system dynamics, x dot is equal to f of x, and your observed variable y is some x plus some xi sub 0. So I'll be using the Greek letter xi to represent noise in all of my slides over here. So the observation is just the true system dynamics plus some sort of noise. But what's key is that in the case of observational noise, the true trajectory is always near the observed trajectory, right? So if I observe something that looks like this, I know that it's actually coming from a clean signal that doesn't look very different plus some noise. So whatever trajectory I have over here is always going to be in the neighborhood of this trajectory, right? And of course, this is true irrespective of the spectrum of the noise. I mean, here I have some sort of white noise, but you could also have some sort of colored noise where it does perturb this trajectory in slightly harder to filter out ways, but really my trajectory is still going to always be close to this trajectory, right? And this is what makes observational noise a relatively simpler problem, right? There are all sorts of methods. For example, you can just use simple spectral methods and filtering if the spectra of the noise in the clean system are quite distinct. But even otherwise, there are all sorts of other methods. There's independent component analysis, there's Kalman filtering, you can do some locally weighted smoothing. Now, all sorts of other things can be done to really filter out observational noise, right? So that's a pretty relatively well understood problem, right? Dynamical noise is a different beast altogether. You see, what's happening in this case is that you have some sort of true system dynamics, x dot is equal to f sub c of x. But the system dynamics that you actually see are x dot equal to f of x comma xi. So my xi is now providing a continual stochastic forcing to my dynamics. And so for now, I'm just going to assume that I am observing my entire system state, and I'm going to assume that I have no observational noise, and I'm just looking at dynamical noise, right? So because I now have a continuous stochastic forcing, the trajectory doesn't remain close to the true dynamics. So over here, this blue curve that I've shown over here is basically a trajectory from the Lorentz attractor. Might be familiar. This curve might look familiar to some of you, but essentially just the x variable of the Lorentz attractor. And you can see it has this characteristic kind of dynamics where it oscillates for a few times in one direction, then it flips and oscillates in the other direction. And what you'll see is that all the oscillations just increase in amplitude because there's an unstable fixed point at the x value in between over here and over here. Now, when you actually add stochastic forcing, when you actually add a noise term, depending on the choice of noise and the various timescales associated with this noise, the dynamics can just be qualitatively completely different. So for example, over here in black is now a curve with dynamical noise. And you can see the trajectory spends this absurdly long amount of time just circling about what is actually supposed to have been an unstable fixed point before flipping around, and then just again spending long amounts of times as well near these unstable fixed points. And this is the clean system will never give you any trajectory that is anything remotely like this, right? And so in this sense, your trajectories are just not going to be close to the true dynamics, right? And indeed, any hopes of even obtaining a true trajectory are really just meaningless, right? Because it is a chaotic system. You just can't obtain a true trajectory. The best you can hope to obtain is the true dynamics. And we're going to quantify true dynamics as being meaningful via what we like to call the climate, which is essentially just time invariant properties of the dynamical system, which could be, say, the measure of the attractor overall. It could be, say, the distribution of the attractor projected along onto some surface. It could be, say, the power spectrum of the trajectories. And really, you can describe a bunch of other parameters as well. And you can really quantify this climate as well. But unfortunately, I won't have time to get into that right now, but I'd be happy to talk about that later. So what we're going to hope to obtain is what we're calling the deterministic skeleton system of the data. So you have data which is coming in some kind of noisy, stochastically forced fashion. What we're hoping to obtain is some deterministic skeletal system that underlies the data that you obtain, that you're observing, but is a deterministic system and has no stochastic forcing, right? And so in this kind of a context, the deterministic skeleton that we hope to obtain by looking at data Y is going to be this true dynamics X over here, right? Okay, so before going to actual examples, let's just look at what kind of forms can the coupling between F sub C and Xi take, right? What kind of couplings can there be, right? And so our primary consideration is just going to be noise, things that look like this, where if I set the noise term to 0, that's equivalent to taking the ensemble average, right? My slides seem to have gotten stuck for a moment. Okay. Now I should say that this doesn't have to be true. For example, if you had a noise which was getting squared before perturbing the system, then setting the noise to 0 would not be the same as the ensemble average. But let's ignore that for now. I can eventually talk about that if we have more time later. But what we're going to look at primarily for right now is this case where taking the ensemble average of the noise is the same as just setting the noise term to 0, right? And what we're going to do is we're just going to take the reservoir and use it in the typical prediction architecture. We're just going to train it to learn the next time step map. And in testing phase, we'll just run it in a closed loop, right? And so an example system, we'll just take the Lorentz model again. This is what its attractor looks like as a clean system. You have this kind of an attractor. This is what the trajectory looks like. And the power spectrum has these peaks. If I look at the power spectrum of the Z variable, and the histogram of the X variable looks something like this, right? It's a trimodal distribution. If I now inject noise into the system, it completely qualitatively changes the system. The attractor looks all messed up. My trajectories are quite noisy. And all of this fine structure of peaks in the power spectra has gotten washed out. And my distribution has become bimodal instead of trimodal, which is really a qualitative change in my system. Now, if I take my reservoir I just train it on this noisy data and I run it in the closed loop, it'll actually just clean it all entirely up. So the reservoir output, after having trained on just the noisy data, recreates the tractor that you originally had, recreates trajectories that look like the original system, and you can really say that the power spectrum and the histogram match almost perfectly. And this is without having any access to the underlying truth. And indeed, this works even very well for large deviations from the original attractor. I can change the time scale of my noise to make it slower or faster. And in this case, if you actually slow down the times of the noise sufficiently, you get these really absurdly long trajectories around these unstable fixed points. And you can see that the autocorrelation of the data has much, much larger time scales than the underlying clean system, but the reservoir can just find those underlying clean time scales very easily, in fact. And really this on a log scale. So you can see that the difference in time scales is very, very large. And once again, if you look at the histograms, you can see you have these really two sharp peaks in the data, but only looking at this data, the reservoir can really reconstruct the underlying system. Okay, so now I'd love to be able to talk more about exactly why the reservoir can do this. But I'm afraid I'm probably going to be running a little low on time at this point. So essentially what I just want to give you a very high, sorry.
I said, the time is wound down, Sarthak.
Yes, yeah. So basically, I mean, we can do some math, which I'd be happy to talk to people after the talk, which can basically tell you why you can actually filter out noise. Maybe that's really what's going on over here. So we see that reservoir computers can reconstruct underlying deterministic dynamical skeleton systems. It's very effective at filtering both white and color dynamical noise. And because this was just when you were trying to treat the reservoir just in the usual prediction task, potentially this explains why reservoir computers work well for link inference, even when working with stochastic real-world systems such as C. elegans. With that, I'd just like to put all of my conclusions up again. These are the papers which discuss the link inference technique. And I'd like to thank you and take any questions at this point.
Thank you very much, Sarthak. It was an exciting talk, and sort of especially the last few slides which you rushed by, and but I guess it was inevitable. There's so much material in your talk that is of so much utility. I'm going to request anybody who wants to ask a question to do so with the following format. Please identify yourself and, if possible, write your question also in the chat box so that it's clear in at least two different modes. Let me, however, start by asking you, Sarthak.
Yeah.
This impressive ability of reservoirs to filter out the noise and give you the underlying dynamical system. What happens if the dynamics has got intrinsic noise rather than, in a sense, what I see is a lot of extrinsic noises. But what happens if the system is inherently noisy, where the fluctuations are really a consequence, let's say, small systems? The cellular dynamics or what have you, you take some situations like that. What if there is no regime where there is determinism, so to speak?
Yeah, I mean, that's an absolutely wonderful question, right? And so, well, what I'm trying to basically try to say is that there exists a deterministic skeletal system, which I didn't really get into defining really for lack of time. But the idea is that we believe that there does exist some deterministic system that is the closest possible deterministic system to that stochastic system. And really, I mean, essentially at the end of the day, any system that you're describing as well could really just be written in this fashion, right? I mean, irrespective of what kind of noise, what the source of the stochasticity is. And I know I kind of showed examples where my noise was just appearing as some kind of simple additive term, which might give you the feeling of like a separate noise. But if I just show an example of what I would have been able to talk about with some more time, is systems that have noise that look much more complicated like this, right? So for example, I can add like a multiplicative noise term, where my noise is really inherently tied to the x of my
multiplicative values. Actually, in there.
Yeah. So it turns out that even if you have multiplicative noise, even if you have noise that doesn't average to 0, where you can have like a chi-square term, you can still access the exact underlying clean system. And turns out reservoirs can do that, and we can really prove that they can do that.
I mean, this is, this is so magical. If this was a TV show, you've fooled me. Right. But I see that there are some other questions that are going on. Would you please identify yourself and ask?
Ram, this is me. May I ask something?
Yes, of course.
Yeah. So, Sarthak, thanks for your talk, and even more so for participating so enthusiastically. So, my question, I have lots of questions, but I just want to ask one small one here, which is that the way in which your network is linked up, are your links one way or two way?
I talking about the reservoir computer itself, or are you talking about like
yes,
in our network itself?
In the reservoir.
In our reservoir computer itself, this is unidirectional link. So the matrix of the reservoir is just randomly populated.
Okay. Is there any specific reason for doing that?
Not particularly. I mean, we have found in practice that there are a lot of possible design choices that you could make in this network that don't affect the capability of the reservoir to a very large extent. I mean, you can really mess around with the degree, and you can mess around with all sorts of things, and they don't make too much of a difference. I think as such, even if you went to directed, bidirectional links, in practice, it really doesn't make too much of a difference to the reservoir as such. I haven't particularly done that, but at least working with reservoir computers, I feel like it won't really make much of a strong difference either way.
Okay, so that's your gut feeling.
Yeah.
Yeah. So yeah, I have lots of other questions, but maybe we'll talk in one of the rooms later. Yeah.
For sure.
We have a breakout where we can talk about these things. Other questions, please?
Hello, Sarthak. I have one question. My question
is just a second, please. I request you just identify yourself so that we know who's asking. And
okay, sorry. So shall I continue or?
Hello.
Hello. So my question is, I want to apply this concept in trading market. There is a big time series data. I want to know what is the next, value. So is it applicable? I mean, how I can apply this to that application?
I mean, I think that is almost literally the $1 million question, isn't it? If you could indeed, of course, forecast stock values and trading data, then I'd probably be making a lot more money, and I wouldn't just be a postdoc over here. Really, these systems are very, very complex, right? I mean, they're extremely, extremely high dimensional systems. So being able to model them and forecast them with anything that I can do on my laptop or even a cluster is going to just be quite unlikely. Now, of course, hedge funds try to do something like this, right? I'm not privy to what other techniques they use, but really in practice, it's just very hard to do just because of the high dimensionality of systems such as, stocks and the market.
Let us say, assume I have super, from India. I was working in SIDAC. So let us say, and I want to clear the noise. And I want only real input, in past, so that I can predict the future value without considering the noise. So is that possible if I have sufficient hardware and all?
In principle, yes. But in practice, the underlying clean deterministic system in that case is also already very, very high dimensional. So I don't think practically you'll be able to do it. In principle, probably, yeah. But it's hard to really say for sure.
But if there is a dynamical system, right? There is a question from Rituparna. If you'd like to speak, go ahead.
Yeah, hi. So my name is Rituparna. So I actually wanted to know that can you use a low pass filter kind of system for, to filter out the noise from dynamical systems, like for both intrinsic, that can be used for both intrinsic and extrinsic kind of noise. And
well, so if you use a filter, the only kind of noise that you can really filter out is observational noise. Because really, I mean, a filter is not going to vary your trajectory a lot. And as you can imagine, there's no filtering of, let's just go back a little bit. I mean, there's really going to be no filter that you can apply on the black time series that will give you the red or the blue time series, right? The trajectories are just far too different. So filtering, low pass filtering or band pass filtering is very effective for observational noise, but dynamical noise is just a different beast altogether. You just can't tackle that with spectral methods at all.
Okay, thank you.
Yeah.
Any other questions? If not,
I think
Colin,
the CC
Sarthak is doing hello.
Sorry to interrupt. May I ask a question? Sarthak?
Sure.
This is Collins.
Go ahead.
So this is Collins from IISER-Pune. Sarthak.
Yeah.
So a wonderful talk. I really enjoyed your work. So I have a question about the first part of the talk where you were inferring networks. Now in C. elegans, for example, you have multiple time scales that are associated with the network. So not only do you have the time scale over which the neurons are interacting with each other through spikes, but there's also neuromodulatory time scales that can be perhaps an order of magnitude greater than the interactions through spikes. And your technique depends on shifting the dynamics of a node by a rather large distinct time scale. So how do you, is there a way that you can deal with something where you have these multiple time scales and you don't a priori know what all of these time scales are?
Yeah, so that is a really, really good question. So the data that we had access to, first of all, we didn't have a lot of data as it is, right? I mean, the data that we had was just of the order of, I think, tens of minutes, right? So it's not very much, but of course there are multiple timescales that exist in the dynamics of the system, and then the question of what are reasonable shifts that you can do, right? So I have to say, I guess a priori, I don't really have a good answer to that question right now. But for the purpose of what we're doing over here, as long as you shift to the time series sufficiently, right, where this sufficientness is larger than the time scales that you have, then you'll start obtaining something that looks like a non-linear distribution. But then there's the question of, okay, how do you know what is sufficient, right? And so what we did in practice was just shift it as much as we could. But of course, if you have much more data, then you probably don't want to do that. You probably want to chunk your data into different regions, possibly maybe by what the behavior of the worm is in different regions at different times and so on and so forth. And you may not have this freedom to be able to just shift it by as much as you want. And that's really like a good question. I don't have a good answer to that right now for how do you really choose these timescales. But in practice, we just shift it by as much as possible.
Also, these data are recorded from a moving worm, right? So you're looking at the motor system. So do you also correlate the behavior of the worm to
so
the kind of dynamics that you see?
That's not something that we were doing in particular, because that wasn't really our primary goal over here. And in fact, the paper where we took this data from by Kato and others, I can probably run to that reference right now. Their essential idea was, their goal was to see if they could somehow connect the data that they observed at the neuron level with the dynamics at the higher scale. So we decided not to really get into that side of things for now and just look at the network inference problem.
Okay.
Thanks.
Shujit, do you still have a question?
Yes, sir. My question is, we can quantify the noise and original signal in your case, right? Mm-hmm. And also, I hope we can identify which is an intrinsic noise and which is not intrinsic noise, right?
To some extent, but it's not always. It's not. You can't always do that. Let me put that. I mean, in some cases you might be able to, but you can't always. Just given access to data, you can't always a priori say how much dynamical noise is there in it and how much observational noise is there in it. As we're arguing over here, you might be able to construct a deterministic system, which will then give you some sort of estimates of maybe how much dynamical noise there is in it. And maybe then you can get to estimating observational noise magnitudes from there. But that's really a very interesting problem that we've thought about and we haven't been able to come to a good answer yet. So
but
a
I
priori,
think,
no, you can't do that.
But I think
But
we can't say directly to that whether this is dynamical noise or not, right?
just given data, it's probably any real world data is probably going to have some mix of both. We don't have a good method right now for separating how much was observational noise, how much was dynamical noise. What we do have a method for is for just cleaning them both out.
Okay, so what my question, like I wanted to build an application where radar or sonar signals can be rectified. I mean, I can extract original signal from the background noise and all. So what do you think, how good it would be if I apply your techniques to that problems?
So I think that's going to be, okay, so it really depends on what you want to do with your radar signals, right? So there is certainly observational noise in those signals as well. And I mean, so if you're trying to transmit information, right, through radar, then you're not really, the radar signal is itself not a dynamical system, but is actually in some sort of encoded string of information. In that case, you're not interested so much in the dynamical noise aspects, but you're primarily interested in the observational noise aspects, which can be filtered out by a variety of methods. You can also use reservoirs for that. But a priori, if you're trying to send a string of bits through radar, for example, the observational noise is going to be your bigger headache.
Okay.
If you're trying to send some other kind of information, then potentially dynamical noise is what you want to filter out, and then our methods work well. But it really depends on what your goal is, right? What is the goal that you want to achieve? And our goal was, given data, can we uncover a deterministic system that we can then model later, right? If you have a clean system, you can potentially actually write out some equations, right? So our goal was in that direction. It really depends on what you want to do, but there are a variety of techniques that could be used in either case.
Okay. And last question, it might not be that much relevant. See, I have sequence of data, okay. And sometimes what happens, we have standard functions like, you know, AX or parabolic functions or e to the power X. But in case, let us say we want to build a stochastic equation where I don't have standard function from the data. Like, let us say there is a 10 numbers and I want to build a stochastic equation for that, so that that function can act as a machine that can transform input to output. In our standard function, we can simply AX equals to Y. So giving the value X, we can predict or we can calculate the Y, right? But in case where we don't have any standard function, in that case, is there any way that we can build a stochastic equation from that?
Okay, so it sounds like the setting you're talking about is more of a map rather than an autonomous system, which has other issues associated with it. But at the high level, if this was really a dynamical system rather than a map, and I guess maybe this also applies to a map, what you could potentially do is you could try to use a technique like this to uncover. So whatever effective function there is has some deterministic parts and some stochastic parts, right? And they're jumbled in together. What we're showing over here is that it is in principle possible to extract out the deterministic part, right? And then you can run it autonomously and you can get more data, and then you can try to actually do some model fitting and you can really uncover what the deterministic part is. Once you have the deterministic part, in principle, you might then be able to try to find out what was the missing components of the noise component. And so if you can separate out both of these components, and we're trying to answer at least one half of that question over here. If you can separate out both of them, then potentially you can then later combine them to actually obtain a function that corresponds to this stochastic map that you were interested in.
Okay, got it.
Yeah.
Thank you.
I have one question. Yeah, this is Rituparna this side. Yeah, so I just wanted to know that we know that noise stabilizes many systems, like any kind of noise, be it additive or multiplicative noise. So in this kind of a system, suppose you have a dynamical system, and so you have both the dynamical noise and the observational noise that is coming into, that is contributing to the overall, that is regulating the overall dynamics of the system. So is there any way to predict or to understand that which of these two noises are sort of stabilizing the system? Is the dynamical noise or the observational noise?
I see. Well, observational noise can't stabilize a system, right? So observational noise fundamentally is noise that applies. So you have dynamics, and then you have some instrument that's measuring it, and you can think of observational noise as lying in that instrument. So fundamentally, observational noise can't stabilize the dynamics of the system. The only kind of noise that could potentially then stabilize it is dynamical noise. And that's kind of like what we were seeing over here, really. I mean, the noise is kind of stabilizing these unstable fixed points. But really, dynamical noise can do that, but observational noise can't quite.
I was asking from a point of neural
resonance.
networks. So where you have like both in a realistic neural network where you have synaptic noises, and those we consider to be sort of extrinsic noise, and there are some inherent noises which are like which are getting generated within the neuron because of its own dynamics. So I was trying to
so both of those are really dynamical noise. So they aren't dynamical and observational noise. They're really both dynamical noise, but they're really two different forms of dynamical noise. One is in the interneuron coupling, and one is within the neuronal dynamics themselves. And really, I mean, trying to separate both of those two is probably a hard question. I think just from the data, separating the effect of those is probably a hard question, which I can't think immediately of a way to approach that question, but that is potentially something to think about. But I don't have a good answer for you immediately. Ram, you were saying something.
Yeah, no, I was going to say that, Sarthak, there is this phenomenon of stochastic resonance where there is extrinsic noise which somehow improves signals. But these are questions perhaps we can take up tomorrow evening at our breakout session. But maybe you think a little about it, and I will also. Maybe this is one issue that we can come back to: unraveling of intrinsic, extrinsic noises, and whether at all one can figure it out when you don't know the underlyings. Yeah.
Yeah.
This is a good point to stop the morning's set of lectures. We come back this afternoon at 2:30, 2:40 to listen to Professor Klaus Lehnertz. So until then, we go into limbo, and we'll be back at 2:40 this afternoon. See you all then.